Okay, let us continue with our discussion of the history of the atom. We've started off with Democritus, and he said atoms were indivisible and indestructible. And then we came to Thomson, and Thomson said, hey, atoms are kind of like a plum pudding. There's a big mass of positive charge, and electrons are stuck in there like electrons. Then we come up with Rutherford's model. He says, hey, there's a positive massive nucleus, and somewhere outside of the nucleus are electrons, and the atom is essentially empty space. And now we're to Niels Bohr, and Niels Bohr happened to be a student of both Thomson first, and then later Rutherford. Good. Now, Bohr was a young man from Denmark, Copenhagen area. He was in his youth a good athlete, a soccer player, but he is also very brilliant. And he comes to Thomson first, and he's trying to figure out what most people are trying to figure out, and that is to explain these lines, which are called the atomic emission spectrum for hydrogen. And what was interesting to people is that these lines were always the same for hydrogen. When you looked at hydrogen, so you have your eye here, right? And you have a spectroscope, and then you have hydrogen in a tube, and you excite that tube, and it will glow, and then you would see these lines. Let's put a nose and a mouth here. Good. So you'd see these lines, and these lines would be somewhere along the lines of 430 nanometers, 490 nanometers, and maybe 660 nanometers. And if you had your spectroscope properly aligned, you'd see these same lines all the time. And the scientists around 1910 were always all trying to figure out, why is this? Well, Bohr takes this idea and he starts thinking about what Planck has to say, and he comes up with an idea of how to explain this. And here's what he says. Well, the first thing you have to understand, I guess, from Bohr's thought is what can cause these lines? Well, that means what? Energy has to be emitted somehow from an atom. And so how is energy emitted? Bohr said, well, I have an electron, I have a nucleus here, and I have an electron, and that electron gets hit with some energy from somewhere. In this case, from the electricity here, electricity. And that electron then would jump, it'd gain energy and move farther from the nucleus. So this electron would jump up here, farther away from the nucleus. But then that electron, after that energy is removed from it, would fall back to its original spot. And what would happen when that electron would fall back? Well, a photon of energy would be released. And we'd see that as light. And so he thought that, hey, these things represent photons from electrons dropping. Okay, good. So that's a good first step. But the question is, why were they always the same energies? In this case, wavelength, but wavelength is related to energy, right? So why was this always 430 nanometers? Why was that always 490 nanometers? And why was that always 660 nanometers of wavelength? And he comes up with this idea. So let's erase some of this. He says, not only do we explain the light, the photons that way, but if these are always the same, that means the drops that the electron is going through must always be the same, meaning electrons cannot be everywhere in the atom. They can only be at certain energy levels, he called them. N equals 1, N equals 2, N equals 3, N equals 4, and so forth. And then, so he said these would be orbits that an electron could be here, electron could be here, electron could be here, electron could be here. And this would be circular in nature, okay? But an electron could not be in between here. That's not permitted, Bohr said. And an electron couldn't be here, and an electron could not be here. and an electron could not be there. So that's why Bohr would say, hey, it's always going to be 430. Why is it always going to be 430? Well, an electron, actually out here at n equals 5, we have n equals 5. I have an electron out at n equals 5. Let's get rid of all these others because, okay, so here we go. Here's my hydrogen. I have an electron out here at n equals 5. What happens? It drops back, and in this case, it drops back to n equals 2. And when it drops from n equals 5 to n equals 2, what happens? It emits a photon of energy, and that photon has a wavelength of 430. So every time an electron drops from 5 to 2, a photon was released. What happened if an electron dropped from 5 to 3? Well, another photon was released but has a different energy. What happens if it drops from 5 to 4? Well, another photon is released but a different energy. But it's always the same step. If it's the same step, then you're always going to get 660 nanometers. If it's always from n equals 5 to n equals 2, you get 490. Now, if it could go from in between to in between, we'd see lines all over the place on this. But we don't see a continuous spectrum. We only see a line spectrum. And so that's how Bohr comes up with his idea of the atom. And let's see if we can summarize Bohr's quantize, because these jumps are based on quantum of energy. Okay, so Bohr's quantized atom. Okay, so what is Bohr's quantized atom? Number one, electrons surround the nucleus. So they're not in the nucleus, they're somewhere outside the nucleus. Good. These electrons occupy orbitals. Can only occupy, he called them orbits at the time. These orbits have a fixed specific amount of energy, or represent a fixed specific energy. We'll call it energy level. Okay? These orbits have a fixed specific energy level. To change levels, let's be more specific. To jump levels, an electron must do what? Absorb a quantum, quantum is singular, a quantum of energy. And here he's using Planck's ideas, right? To drop energy levels, we'll make sure we clarify that, energy levels, electrons must emit, right, a quantum of energy. And finally, he defines something called the ground state. The ground state for an electron is the energy level closest to the nucleus, representing its lowest possible energy. Okay, that is the ground state of an electron. There is then also something called an excited state. And that is, the excited state is any energy state of an electron farther from nucleus, from nuke. If it's farther from nuke, that means higher in energy than the ground state. Okay? State. Whoo! Wow. So that is Bohr. And like I said, I hope you do not find this boring, because I find it very interesting. Okay, so just summarizing. Electrons surround the nucleus, right? Good. Electrons can only occupy certain orbits. They can't be everywhere. They can only be in what he called certain orbits. Orbits have a fixed specific energy. Good. To jump levels, electrons must absorb quantum of energy. To drop levels, electrons must emit a quantum of energy. And then finally, the ground state for an electron is the energy level closest to the nucleus, representing the lowest possible energy of that electron. An excited state is any energy state of the electron farther from the nucleus and higher in energy than the ground state. Wow. Well, that is Bohr's model. Let's see, how are we doing on time? Let's go with one other guy. I think we can get one more guy in before we start getting too far into this. Now, after Bohr, well, let me add one more thing about Bohr here. Bohr does this all when he is 28 years old. He's a young guy, wins the Nobel Prize. He wins the Nobel Prize the same year as Einstein, and that was 1922. Okay, good. So let's go to our next guy, Louis de Broglie. Louis de Broglie is a Frenchman, and he's extremely interesting. All these guys are interesting, but what makes him fascinating is he is true royalty. Royalty. I've never been a big fan of royalty. I thought they really didn't do much but sit around and live off the back of serfs. But de Broglie's different. I mean, his family for generations had served the French kings as advisors. Um, his brother was supposed to go into that, but his brother loved physics. And so he actually took his home, that one of their castles, and built a physics lab in the basement. And his little brother, Louis, started learning physics in the basement of his older brother's palace. And what makes de Broglie even more fascinating is he didn't study physics. He studied medieval history at the Sorbonne. Sorbonne. So he studied medieval history, and he didn't even study physics right away. He goes into World War I, and he actually works with radio waves. And this is really, I think, the key. Maybe also, he is also a big fan of chamber music. And if you know anything about music or about radio, you understand that both things have to do with what? Waves. Now, at this time, after Bohr, people accepted Bohr's ideas, but they couldn't explain why electrons could only be at certain orbitals. Certain orbits? Why did they have to be only in those places? And de Broglie applies this idea of waves to electrons. Remember earlier, in our last earlier in this unit, we said what? Energy has a wave particle duality, right? That means energy has wave characteristics and particle characteristics. Good. Well, de Broglie takes this idea and flips it on its head. He says, hey, let's assume electrons have wave characteristics. I mean, clearly, electrons already have particle characteristics. They are particles. They're mass. They have mass. They're matter. So he says electrons have wave characteristics, meaning they travel. His idea was that they travel around the nucleus. Electrons travel around the nuke as waves. That's what de Broglie added. And the way to think of this is, okay, here's a wave, right? Well, if I take that and put it into a circle, there's only certain places where it will always match up. That if I'm not in the right place, one time it'll go like that, and the next time it'll go like that, and it won't go right over itself. It won't align properly. That there are only certain areas where this tail will always hit that tail if I bend it in a circle. And those turned out to be exactly what was predicted by Bohr's atom. And so that's how he was able to explain why you'd have n equals 1, n equals 2, n equals 3. That would be the location where the wave ends would meet and constructively align, I guess you could say. Okay, I'll tell you what, we've got 3 people left, but this is probably good enough for this lecture. So let's see you next time for part 3 of the history of the atom. Bye.